Alright, a new scene after some drop-in visitors, little helpers. Alright, I've redrawn the load line and the characteristic curves to make it a little bit clearer there, and this time I've also added some representative audio waveforms. Now, when we put audio into this circuit, coming in through a DC blocking capacitor, it's important to understand that you need a DC blocking capacitor there, because otherwise the signal generator would change through its resistance, would change the voltage on the base, and we don't want that to happen, so we do need a DC blocking capacitor. But the audio at 1 kilohertz could go straight through that capacitor, and it's going to add to the base voltage and subtract from the base voltage at that 1 kilohertz frequency. So by slightly changing the base voltage, only just a fraction up and down above the turn-on voltage for the transistor, we're therefore increasing the base current slightly and decreasing the base current. So on the set of characteristic curves here, I've shown that we're increasing the current and we're decreasing the current. If we're changing the base current, especially if we're increasing the base current, we're going to increase the collector current. Increase the collector current by the factor of beta. And beta for this transistor was 280, I think, from memory. So little tiny change in the base current is going to make a dramatic change in the collector current. Now, it's important before I go to this part of the graph, what's happening to VCE, to understand that when the collector current increases, maybe what I'll do here, I'll draw that resistor in. Here's 4.7K. This is RC. And I've got plus 12 volts. And I've got, what can we put here? We'll put a current meter here. And down to ground. And when we're at saturation with the transistor, we had 2.55, I think it was, 2.55 milliamps of current. Simple Ohm's law. So I equals V on R, 12 divided by 4.7K, and 2.55 milliamps. So when the collector current reaches 2.55 milliamps, I'm going to have the complete 12 volts dropped across that resistor. And if I had another sampling resistor here and I measured voltage across it, I'd be measuring nothing. It'd be a short circuit. So this dynamic junction resistance across here, and that's what we have got. I'll just redraw that as an inset. Collector, emitter, and we've got this variable resistance across here. And when the collector current gets to the saturation point, or even if it increases, the effect of that junction is that the resistance gets smaller. So therefore, the voltage across that junction gets smaller as the collector current increases. Now, this is a very hard concept for students to understand. But if we come back to the characteristic curves, base current increasing, maximum on the signal, collector current increasing, maximum on the signal, up here, and at the same point in time, VCE coming down to minimum. Collector current maximum, more voltage dropped across the collector resistor, so therefore we've got less voltage across the junction of the transistor. And this is simple Kirchhoff's voltage rule. The fact is that the sum of the voltage drops in the circuit has to equal the supply voltage. If we get more voltage dropped across the collector resistor, we'll have less voltage dropped across this dynamic resistance of the collector-emitter junction. And look, I asked this question many times in classes to students, why when the base voltage increases and therefore the base current increases with the AC waveform which is going in, why do I get the inverted waveform on the output? Why do I get this? And that's the fact of the situation that I've just explained. The fact is that more voltage is dropped across RC, therefore less voltage across VCE. And if we're measuring from this point here or this point here, we're seeing the voltage across VCE dip as the input voltage and therefore the input current rises on the base. So that's a very, very important concept to understand. The load line and setting the quiescent point. When we do have an AC waveform that we want to amplify and use this transistor as an amplifier, we really need to pick the base resistance carefully so that we set the Q point. Q point along the load line to about half of the rail voltage. The rail voltage here was plus 12 volts. It'd be nice if we set the collector voltage at 6 volts in the resting state. So I want that to be around about plus 6 volts in the quiescent state. That way, that 6 volts can go, let's say here's 6, plus 6, we could go up to say plus 8 and down to down to plus 4. So we could have a 4 volt peak to peak swing and we won't hit the rail and we won't hit ground. Now if we put too much input voltage into here and we make the base current increase and decrease too much, this is what's going to happen. We're going to have a bigger waveform here, a bigger change in base current, and therefore we'll have a, oh dear, it's trying to go up here, but we've already hit saturation. It can't go any further. Oh my. So, and maybe the other thing, the other extreme too, maybe we're going to hit down here. Oh, saturation. Oops, sorry, that's cut off. No, that's saturation. This one will be cut off. And then back around again. Oh my. Look at this, and we call this clipped. It's clipped at the here, top clipping, bottom clipping. Symmetrical clipping. Sometimes, if the Q point was shifted on the load line, we would get, I'm running out of space here to squeeze things in, we'd get asymmetrical clipping. Because the whole input waveform is going to be up here and the output waveform is going to be shifted higher. We've got top clipping and we'd still have a nice sine wave on the bottom. Don't know if I can attempt to draw that. Maybe in red here. Up, flat, and then this part here though, okay. So no clipping at this point because we didn't actually get down to VCE 0 down here, but we didn't actually get down to the VCE off point down the bottom, but we certainly did hit saturation with VCE equals 0 at the top here. The board looks a bit messy, but this does happen, of course, when we're playing with load lines and transistor amplifiers. Now, other things that will come out when I do the little lab with that board, we're going to heat up the transistor. So Q1, the BC108, we're going to heat it up with a small oven, and we're going to see that we actually make the transistor turn on harder, and that's going to have the effect of shifting the Q point. So when we shift the Q point up towards saturation, we're going to find IC falls. So that'll be something to look for in the lab that we do later on today. And then with the audio, we're going to see a little bit of distortion because this type of setup, it's more configured for a switch, transistor switch. Transistor amplifier, it needed a little bit more resistance in the emitter circuit. So I'll show you that, I'll demonstrate that with the oscilloscope as probably a part B to this video. So there'll be the theory part, part A, and then I'll do a part B, which is the actual lab with the board, showing you all those points about what I've talked about in this theory lesson. Again, this is Greg Moore for TAFE New South Wales, wrapping up BJT biasing part 1. In the next video, we'll go on and we'll look at voltage divider bias and collector feedback bias, and we'll see why they're so important to understand.